Right, so in zero order reaction, first we'll see how to derive the expression for rate constant, which we normally represent by the symbol K. I'll put 0 at the subscript, which indicate rate constant for zero order reaction. Okay, rate constant. So this is what we are going to derive now. What is K naught? K naught is nothing but rate constant for zero order reaction. Okay, rate constant for zero order reaction. Okay, let us consider a zero order reaction. Consider a zero order reaction of the type. Let me write a reaction like this: A giving some product. I have a reactant A which reacts to give some product. Assume that this reaction is a zero order reaction. Okay, listen, at time 0, at t equal to 0, let the concentration of the reactant be A naught. Students, observe carefully. A naught is the initial concentration of the reactant. Okay, then at time t, say for example after 10 seconds or after 20 seconds or after 1 minute or after 5 minutes, whatever it is, after time t, let the remaining concentration of A, you know very well, as the reaction progress, concentration of A keep on decreases. Okay, so initial concentration will be very high. As the reaction progress, concentration of A decreases, right? So now at time t, we have some concentration of A, okay, that I represent as simply A. A is the concentration of reactant A, or this gives you concentration of reactant A at the time t. If you want, you can also put T here, nothing wrong in it, which is concentration of A remaining at time t. Okay, now what is the rate of what is the expression for rate constant of this reaction? Listen, according to rate law, you know very well, according to rate law, rate of this reaction, rate, how will you write rate? Listen, with respect to reactant, we can write rate as minus dA by dt. Okay, minus dA by dt, right? What is meant by that? It is nothing but decrease in concentration of A with respect to time. Okay, that gives you the rate. So rate of this reaction, right, is given as minus dA by dt, and according to rate law, let me write here, according to rate law, this rate, that is minus dA by dt, right, is directly proportional to the concentration of the reactant, okay, raised to power the order of the reaction. We have assumed that this reaction is a zero order reaction. We have taken a zero order reaction, therefore order of this reaction should be 0. Okay, this is as per rate law. According to rate law, rate of the reaction is directly proportional to the concentration of the reactant power 0. Why 0? Because it is zero order reaction. Now let me convert the proportionality into equal. Right, when you convert proportionality into equal, we should introduce a constant. Okay, so let the constant be K. I'll represent that K as K naught. What is this K naught? K naught is nothing but rate constant for the zero order reaction. Rate constant for the zero order reaction. And here we have concentration power 0. Anything power 0 is 1, you know. Right? Anything power 0 is 1. Therefore, we can write this as minus dA by dt equal to rate constant for the zero order reaction. Okay, now what I'm going to do, I'll bring this dt to the right hand side. So we get, Let me go to the next page.
So 1 minute, sir.
One second, yeah. It is very essential that everyone must write. Okay, just by seeing this derivation, you won't get the clarity. Keep a notebook with you, and you also derive along with me so that you will remember this. It's an easy way of learning concepts. Okay, then finish?
Yes, sir.
Okay, ma, right. Now, so in the last step we had minus dA by dt equal to k naught. I'll bring the dt to the right hand side, so we get minus dA equal to k naught into dt. Okay, now what I'm going to do, see, dA means small change in the concentration of A, very small change. Okay, so we want to know what is the change up to time t. So what you have to do, you have to integrate. Okay, students, observe carefully why we are integrating. Right here, dA or dt, this dt represents small change in time, but now we have carried out the reaction from 0 time up to some time t. This may be 10 minutes or this may be 5 minutes. Okay, so from 0 time to 5 minutes, okay, in every second, right, the rate of the reaction is different. Initially, reaction may occur faster, but as the reaction progress, concentration of the reactant decreases, so rate also decreases. Okay, so to find the total change, okay, you need to integrate this, because you can also take summation. Student, observe carefully, you can also take summation. When you will take summation, if the change in rate is same in every second, then it is correct. But here the change in rate is not same, or the rate decreases, okay, in a different manner. As the time progress, rate is not constant, you can say in the other way. Okay, therefore you need to integrate this expression to find the total change. So I'm going to integrating this equation. On integrating, what will get? I'll keep minus sign out. Integral change in concentration of the reactant dA equal to, I'll keep this constant out. K naught is constant. Then integration dt. What's the limit? Yeah, we start the reaction at time 0, and we are finding the change up to time t. So the time interval is 0 to t. When time is 0, the concentration of the reactant is A naught. Am I right? When time is 0, concentration of the reactant is A naught. At time t, the concentration of A is AT. A naught is the initial concentration, and AT is the concentration at a time t. Okay, and you know very well integral dx. What is integral dx? Integral dx is x. Okay, therefore here instead of dx I am having dA. So integration of dA is, I'll keep this minus sign as such. Integration of dA is A, right? And we have two limits here. We have two limits. The upper limit is AT and the lower limit is A naught. Okay, I'll keep this K naught out, and integration of dt in a similar manner will give t. Upper limit is t, lower limit is 0. So what I'm going to do, in the place of concentration, first I'll put the upper limit. Okay, I'll change the bracket sign. I'll put the upper limit. So in the place of A, I'll put upper limit AT, minus in the place of A, I'll put the lower limit now. Okay, equal to K naught into, similarly in the place of t, first I'll put the upper limit. Upper limit is t. Then in the place of t, I'll put the lower limit, which is 0. Right? So if I multiply by minus sign here, what will I get? Minus AT plus A naught equal to K naught into T. Okay, or I can also write this as K naught into T equal to A naught minus AT. See, I wrote the first positive sign first, then negative sign term in the second position. Okay, then what is K naught? Rate constant for zero order reaction equal to initial concentration of the reactant minus concentration of the reactant at a time t divided by T. This gives you rate constant for zero order reaction. Students, take down this. This is the expression for rate constant for a zero order reaction. K naught equal to A naught minus AT by T, where A naught is the initial concentration of the reactant, AT is the concentration of the reactant at a time t divided by T. T is the time. Okay, or time taken. Is this clear? Any doubt? This is a very simple integration. You might have seen this in your mathematics class. Is this clear, student? Any doubt?
Clear, sir.
Right. Now let me go to the next step. Yeah, see here. So rate constant K naught equal to initial concentration of the reactant minus concentration of the reactant at a time t divided by T. Okay. Now let me do some rearrangement here. I'll bring this T here, K naught into T. Remember, this is the expression for the rate constant for zero order reaction. Okay, now I'll bring this T here, K naught into T equal to A naught minus AT, or I'll bring this minus and this minus term to the left hand side and this term to the right hand side. So I'm making some small rearrangement. AT equal to A naught minus K naught into T. Is this clear? Is this clear, student? Now, how to find the rate constant of a reaction? Okay, I need to calculate the rate constant. How to do that? Very simple. You can get this by plotting, okay, concentration of the reactant at a different time versus time. Okay, which is something similar to y is equal to mx plus c. This equation is similar to the equation of a straight line. Y is equal to mx plus c. So I am plotting concentration of A at a different time, or concentration of A at a time t in y axis and time in x axis. Students, since it is a straight line and see the slope is negative. Okay, m is slope is equal to k minus k naught. Slope is negative. So you'll get straight line with a negative slope. It will go like this. You'll get a straight line with a negative slope. And this point will give you the initial concentration of the reactant, because this is at time 0. At time 0, the concentration of the reactant is A naught. Then as the time increases, okay, concentration of A decreases linearly for zero order reaction. Students, observe carefully. This change may not be linear for other reactions. Keep this in mind. This change may not be linear for other reactions. So if you get a straight line with a negative slope, that corresponds to zero order reaction if you plot A versus T. Okay, and the slope of this straight line, slope of the straight line, which is nothing but m, will give you the value of k naught. So what is k naught? K naught is nothing but negative of the slope of the straight line. So from the graph you can evaluate the value of the rate constant. From the graph you can evaluate the value of the rate constant for zero order reaction. Right, students, is this clear? Any doubt? The point you have to
Not also.
yeah, good ma. The point you have to remember here is, for zero order reaction, if you plot concentration in y-axis and time in x-axis, you will get a straight line with a negative slope, and slope is equal to minus k naught. So if you know the slope of the straight line, you can find the value of k naught, right? Then next term, okay, what is the unit of k naught? Anyone? Can you tell me what is the unit of rate constant for zero order reaction? This we have already discussed.
Moles per liter per second.
Very good. Yes, unit of k naught, rate constant of zero order reaction, is equal to unit of rate of the reaction. Unit of rate of the reaction. Very simple. What is the unit of rate? Unit of rate is mole per liter per second, and this is the unit for the rate constant for zero order reaction. Note down. So for zero order reaction, the unit for k naught is mole per liter per second. You can also write like this. Sometimes people will write like this: mole per liter is molarity, so molarity per second. Like this also people writing. That is also correct. Okay, molarity per second, mole per liter per second, or molarity per second. This is the unit of rate constant. Then next important point is half-life. HALF, half-life period or half-life time of a reaction. Half-life period, half-life time or half-life period of a reaction, which we represent by the symbol T half. T half. Okay, what is meant by half-life period of a reaction? Students, it is nothing but time taken for the 50% completion of a reaction. Say you start some reaction with some initial concentration, say 1 molarity, carry out the reaction. If the concentration of reactant become 0.5, okay, the time taken to reduce the concentration from initial to 0.5 is nothing but half-life period of the reaction. Okay, so let me write here like this. What is half-life period? Half-life period of a reaction, right? Half-life period of a reaction is the time taken for 50% completion of the reaction. Very simple. Half-life period is nothing but the time taken for 50% completion of a reaction. Okay, suppose if I start with 1 molar initial concentration of a reactant, then you see what time is required for the concentration to become 0.5. Okay, it's called 50%. That time is nothing but half-life period of the reaction. Okay, now what is the half-life period expression for zero order reaction? Right, then for zero order reaction, okay, what's the rate constant expression? You know very well, k naught equal to initial concentration of the reactant minus concentration of the reactant at time t over t. Okay, students, observe carefully. This is initial concentration, right? When t become t half, see, when time become half-life period, what will happen to the concentration of the reactant at time t? Right? Concentration of the reactant at time t becomes equal to A naught by 2. Is it correct? What is AT? AT is the concentration of the reactant at time t. When time become half-life, what will be the concentration of A? It is half of the initial concentration, am I right? Okay, so initial concentration is A naught. A naught by 2 will give you the concentration of A at the half-life. So now I am going to put those values here. So therefore, I'll get k naught equal to, I'll keep this A naught as such, minus, in the place of AT, I'll put A naught by 2. A naught by 2 whole divided by t. When t, here t become t half. In the place of T, I'll put T half. A naught, see the numerator, A naught minus A naught by 2. What we'll get? A minus A by 2, like that. A naught minus A naught by 2 is A naught by 2. Therefore, let me write the next page. Or I'll write here itself. See, the numerator we have A naught minus A naught by 2. If we subtract, I'll get A naught by 2. So we can write this as A naught by 2 into T half. Now I'll bring the T half to the left hand side. So let me write the next page. I'll just make a small rearrangement here. So T half for a zero order reaction, T half equal to initial concentration of the reactant divided by 2 into K naught. Take 2. Take 2. This is for zero order reaction. See, 2 is a constant, K naught is constant. So I can also write this as T half is directly proportional to initial concentration of the reactant. Students, observe carefully. For zero order reaction, half-life period is directly proportional to initial concentration. As initial concentration increases, half-life period also increases in the case of zero order reaction. Note down. Right? This is for zero order reaction. Note down. Is this clear, student? Any doubt? Students, is this clear?
Yes, sir.
Right? Yeah. See, in zero order reaction, these two things you should remember. If I plot, students, if I plot A naught, or sorry, AT versus T, what type of graph we'll get? Concentration of the reactant versus time. What type of graph we'll get or plot? Students, the equation is this, no? AT equal to A naught minus K naught into T for zero order reaction. So if you plot, you'll get a straight line. You'll get a straight line with a negative slope. You'll get a straight line with a negative slope. Okay, this is a characteristic plot for zero order reaction. Okay, and slope, from the slope we can find the value of K naught. So K naught equal to minus the value of the slope. And second important point is that if I plot rate versus concentration of the reactant, yes, student, how the plot will look like? See, from the rate law, you know very well, from the rate law, we had seen this already, minus dA by dt is directly proportional to concentration of the reactant power 0, right? Okay, or I can write this as minus dA by dt is equal to K naught into concentration, since concentration power 0 is there, so that should be 1. What does this indicate? Minus dA by dt is nothing but rate. What does this indicate? Rate is constant. See, rate is constant, K naught. Rate is independent of the concentration of the reactant. So if you plot rate versus concentration, okay, rate is independent of concentration, so you will get a straight line parallel to x-axis for zero order reaction. Okay, for zero order reaction, rate is independent of the concentration of the reactant. Okay, this is a very, very important information you should keep in mind. Take note. Is there any doubt, student? Is there any doubt? See what quantities we are plotting. In the y-axis we are plotting rate. In the x-axis we are plotting concentration. Is this clear? Students, is this clear? Hello?
Yes, sir.
Yeah, right. So this is regarding zero order reaction. Okay, now we'll do problems and other things in the next class. Let me go to the first order reaction. So this next important one is first order reaction. Take two. First order reaction. In a similar manner, we have to derive the expression for rate constant, expression for half-life period, unit of rate constant, and a graphical representation. Okay, yeah, let's start like this. See, consider a first order reaction. A first order reaction of the type A giving some product. A giving some product, or you can also instead of product you can also write B. A giving B. A is the reactant, B is the product here. Okay, I have a first order reaction like this. Now let us assume that at time t equal to 0, the concentration of the reactant is A naught. What is A naught? Student, what is A naught? Hello student, what is A naught? Kirtana?
Initial concentration, sir.
What is A naught?
Initial concentration, sir.
Yeah. Hello Kirtana, are you listening? Hello? Hello Kirtana, are you listening?
Yes, sir.
Okay. See, at time 0, the concentration of the reactant is A naught. Okay. At time t, okay, you will have some concentration, let it be AT. Because as the reaction progresses, right, concentration of the reactant decreases. Right. So A naught is high value actually. It's a very high value. AT value will be very compared to A naught, it is low, because as the reaction progresses, concentration decreases. Okay. Now, according to what is the rate of the reaction? Rate of this reaction can be written as with respect to reactant, you can write rate of the reaction as minus dA by dt. With respect to product, we can write the rate of the reaction as dB by dt. For reactant, you should put negative sign. For product, positive sign. Now, according to rate law, rate of the reaction is directly proportional to concentration of the reactant power 1, because it is a first order reaction. Rate is directly proportional to concentration power 1. Okay, now what is the expression for rate? In terms of reactant, it is minus dA by dt. So in the place of rate, I will put minus dA by dt. Okay, then let me convert the proportionality into equal. So if we convert proportionality into equal, we should introduce a constant. I'll introduce that constant as K1. What is K1? It is the rate constant for first order reaction. Rate constant for first order reaction into, and here we have concentration of A power 1. Anything power 1 is the same thing, right? So concentration of A I should retain as such. Now I'll bring this A to the left hand side and dt to the right hand side. I'll make a small rearrangement here. I'll bring this A to the left hand side and I'll bring this dt to the right hand side. See, as I told you before, dt is nothing but for small change. If there is a 0.5 second change or even very, very small change. For small change, okay, this is the change in concentration. But in this reaction, see, we are making change from time 0 to time t, okay. some time 0 to time t. This may be 10 minute or maybe 5 minute, whatever maybe it is. Okay, so we are allowing the reaction to progress from 0 time to some time t. Okay, so we need to find out what is the total change in the concentration. To find total change, you need to integrate. Okay, so on integrating the above equation, see, I am going to integrate left hand side minus dA by A. In the right hand side, I'll keep constant outside the integration bracket. So K1 into integral dt. What is the time interval? Initial time 0 and final time is time t. When time is 0, the concentration of the reactant is A naught. At time t, concentration of the reactant is AT. Okay, A naught is the initial concentration of the reactant. AT is concentration of the reactant at time t. Remaining concentration actually. Okay, now we have to integrate this. You know very well, integral dx by x is nothing but ln x. Students, observe carefully. Integral dx by x is ln x. Ln is nothing but, what is ln? Ln is nothing but log base ex. Exponential logarithm. Log base ex is nothing but ln x. Okay, so the above equation, if you integrate, we'll get this. Yes, student, complete this first. Take down. Okay, let me go to the next page. So, if you integrate, you will get ln A. Integral dx by x is ln x. So, in our case, we have integral dA by A. So, ln A. Okay, and in front we have the negative sign. So, I'll keep the negative sign as such. What is the upper limit? Upper limit is AT and lower limit is A naught. In the right hand side, we have K1 into integral dt is t, upper limit is t, lower limit is 0. So first I'll put upper limit in the place of a. I'll keep this minus sign as such. I'll get ln a, ln at. Then before putting lower limit, you should put minus sign, minus. Then in the place of a, you put a naught, lower limit, a naught. Okay, equal to K1, I'm sorry, yeah, K1 into, in the place of t, I'll put upper limit is t only, lower limit is 0, so you need not write that. And here, if you multiply by minus sign, in the left hand side, see, plus into minus become minus, minus into minus become plus. So I'll write the positive term first, ln a naught minus ln at equal to K1 into t. Or we can write this as ln a naught by at equal to K1 into t. Okay, or we can also write this as K1 equal to, I'll bring this t to the left hand side, 1 by t, so you'll get 1 by t times ln initial concentration of the reactant divided by concentration of the reactant at a time t. Right? Student, note down this expression. This is the integrated rate constant expression for first order reaction. And you also know that, students, you also know that ln, okay, suppose I'll take some ln x. Ln x can also be written as log base ex, which is also equal to log base 10x. Okay, but you have to multiply this by 2.303. Students, ln x equal to log x base e, which is also equal to 2.303 times log x base 10. So I am going to convert this ln into log base 10. Okay, so that you'll get k1 equal to 1 by t into, so if I, in the place of ln I'll put log base 10. If you put log base 10, we'll get 2.303 should come in the numerator. So I'll remove this one. I'll put 2.303 by t log a naught by at. Is this clear, student? Any doubt? Students, is this clear? K1 equal to 2.303 by t log a naught by at. If you have any doubt, you can ask me, student. I'm sorry, denominator time is 80. A naught is the initial concentration of the reactant. AT is the concentration of the reactant at a time t. Is this clear, students? Any doubt?
Clear, sir.
Right, ma, take note. Yeah, students, just note down this expression. This is also very important, right? All these expressions, all these three expressions are very, very important. Okay, now let me go to the next page. So now we'll see the characteristics of some the rate constant, characteristics of the first order rate constant. Let me start with the unit. Okay, what is the unit? Number one, unit of first order rate constant, or rate constant for first order reaction. Unit of rate constant for first order reaction. Okay, it's very simple. You know very well the rate constant expression for first order reaction, K1 equal to 2.303 by t log base 10 initial concentration of the reactant divided by concentration of the reactant at a time t. Okay, student, observe carefully. Concentration unit is mole per liter. Here also we have concentration term mole per liter. So mole per liter cancels. Therefore, there is no unit from this part. So we have only time quantity. So only time unit will appear. Okay, and the unit of K1. So time is in the denominator. Therefore, unit of K1 is second inverse or minute inverse, or in general time inverse. But this is the SI unit, so keep this in mind. So what is the unit of rate constant for first order reaction? Second inverse. Okay, take down. Second inverse is the unit of SI unit of rate constant for first order reaction, right? Then we'll see the half-life period expression. Let me go to the next page. If you find any difficulty, please tell me. Okay. Number 2, half-life period. Half-life period, which we represent as T off. Right? You know very well what is the definition for half-life. I have given already. It is the time taken for 50% completion of a reaction. Time taken for 50% completion of a reaction. Okay. Now, when T becomes equal to T half, what will happen? Concentration of the A at time T is becomes equal to A naught by 2. This we know very well. When time become half-life, what will be the remaining concentration of A? remaining concentration is nothing but initial concentration by 2. Okay, now let me go to the expression for rate constant. So what's the expression for rate constant? K1 equal to 2.303 by T log base 10 initial concentration of the reactant by concentration of the reactant at time t. Students, observe carefully. Now in the place of AT, when T become T half, let me write the next page, K1 equal to 2.303. So in the place of T, I'll put T half. When T become T half, okay, keep this initial concentration as such, then concentration at the time T becomes equal to A naught by 2. So I'll put A naught by 2 here. A naught cancel, the 2 will go to the numerator. So you'll get K1 equal to 2.303 by T half into log 2 base 10. Log 2 base 10. Okay, or you know very well the value of log 2. Students, these 3 log values you should remember. Log 2 is 0.3010. People say roughly 0.3, right? Log 3 base 10 is 0.4771. Okay, I'm sorry, I made a mistake. This is for log 5. Log 3 is I'm sorry, correct. Yeah, I wrote correct value, 0.4771 only. Yeah, it is roughly 0.5, roughly. Okay, and log value for 5, log 5 base 10 is 0.6990, log 5. Okay, which is roughly 0.7. Roughly 0.7. Okay, students, these 3 log values are very, very important. If you remember these 3, okay, for other log values, for most other log values can easily be calculated using this. So remember these 3 values. Log 2 is 0.3010, log 3 is 0.4771, log 5 is 0.6990. Okay, then now students, see here we have log 2. The value of log 2 is 0.3010. So K1 equal to 2.303 times 0.3010 over T half. 2.303 into 0.3010, if you multiply, you will get, I'll bring this T half to the left hand side, so T half equal to 0.693. If you multiply 2.303 and 0.3, you will get 0.693, and bring this K1 down. So T half equal to 0.693 by K1. This is the half-life period expression for first order reaction. Note down. T half is equal to 0.693 by K1. Students, is there any concentration term exists in the half-life period expression? See the final expression. Is there any concentration term?
No, sir.
No. That means half-life period of first order reaction is independent of initial concentration of the reactant. I'll write in the next page. Just note down this information, students, very, very important. So half-life period of the first order reaction, let me write here this. Okay, so this is very important point. Half-life period of first order reaction. Right, half-life period of first order reaction is independent of initial concentration. Independent of initial concentration of the reactant. Very, very, very important. Half-life period of a first order reaction is independent of initial concentration of the reactant. Whereas for zero order reaction, see, if you note down whatever we wrote now, listen, you just go through that. For zero order reaction, half-life period is directly proportional to initial concentration of the reactant. A naught will be there. Okay, whereas for first order, okay, half-life is independent of concentration. Right? Note down, student. And remember the expression? The expression is this: T half equal to 0.693 by K1. Or you can also write like this, that is 2.303 times log 2 base 10 over K1. Or you can also write like this, ln 2 by K1. This is in terms of ln, because you know very well 2.303 into log 2 base 10 is nothing but ln 2. So ln 2 by K1 also you can write. All these are one and the same. Take note. Different way of writing the half-life period for first order reaction. Is this clear? Student, any doubt? Is this clear?
Yes, sir.
Yeah, right. Now, let me go to the graphical representations for first order reaction. Graphical representation. Okay. Now, students, let me take this expression first. See, I have told you to remember few expressions in first order. So let me take this in one particular step. We had this equation, A naught by AT equal to ln A naught by AT equal to K1 into T. Just check it. The last two slides before, we had this expression. We had this equation actually. Ln A naught by AT equal to K1 into T. Students, observe carefully. Now I'm going to take the reciprocal of this, A naught by AT. I'm going to change it into AT by A naught. So AT by A naught. When you reciprocate in a logarithmic function, if you reciprocate any quantity in a logarithmic function, the sign of the right hand side will change. Simple. I'm sorry, actually I should not say like that. The sign will change here. You should put minus sign here. See, I'm taking what I'm doing. I'm taking reciprocal. A naught by AT is written as AT by A naught here. Okay. So whenever you reciprocate any quantity in a logarithmic function, okay, the sign of the quantity log will change. Okay. Now you multiply both sides by minus 1. So this become plus. So ln AT by A naught, this is AT, I'm sorry, ln AT by A naught equal to minus K1 into T. Okay, then students, one more information, observe this carefully. Suppose if you have ln X equal to some number, say C. I have some number C. Ln is nothing but, you know very well student, ln is nothing but logarithm of base E. Here we have C, okay. What is the value of X? X is nothing but, bring this E to the right hand side and write this C in the power of E. So X is equal to exponential power of C. Exponential power C, okay. Now listen, see in a similar manner, see this expression student. We have ln AT by A naught, so this is my X, okay, and this is C, so ln X equal to C is there, therefore I can write AT by A naught as e power minus K1 into T. Any doubt student, any doubt in this? Just observe this carefully. Very simple expression, but very, very important. Then what is AT? AT is equal to, I'll bring this A naught to the right hand side, A naught into e power minus K1 into T. Very, very, very important expression for first order. Okay, what is A? What is AT? AT is the concentration of the reactant at a different time t, or concentration of the reactant at a time t. What is A naught? A naught is the concentration of the reactant at the beginning of the reaction, that is at time 0. And what is K1? K1 is the rate constant for first order reaction. Okay, now what I'm going to do, I'm going to plot this AT versus T, which we already done for zero order reaction. Okay, in a similar manner I'm going to do for first order. Okay, so let me write to the next page. Students, observe carefully. So for first order reaction, concentration of the reactant at a time t is equal to concentration of the reactant at the beginning into e power minus K1 into T. Remember this expression. This is the expression for which the expression that gives you the concentration of the reactant directly. Now what I'm going to do, I'm going to make a plot. I'm going to plot concentration of A at a time t in y-axis and time in x-axis. Okay, here time is 0. Suppose, student, tell me what happens if t is 0. If I put t 0 here, what will get? What we will get? If t is 0. If t is 0, the power becomes 0. What is e power 0? E power 0 is 1, correct? So AT equal to A naught. Yes, you are right. AT equal to A naught. So when time is 0, then AT will have some value that is nothing but A naught. That is the initial concentration. Then as the time increases, we have e power minus KT. That means the concentration decreases exponentially, not linearly. Concentration decreases exponentially. In the case of zero order reaction, concentration decreases linearly, right? For zero order. We had discussed already. Whereas for first order, concentration decreases exponentially like this. It decreases exponentially. Okay, note down, student. Very important. So, whenever, if you have linear line, if you have a straight line, you can calculate rate constant from the straight line. But whenever you get exponential curve, you cannot find rate constant directly from this. So what to do? To find rate constant, I will go for logarithmic expression. Okay, take down. Logarithmic expression, we know already that ln this step we had already. Just go through if you want. K1 equal to rate constant for first order reaction equal to 1 by T times ln initial concentration of the reactant by concentration of the reactant at time t. Okay, see here we have logarithm. Now what I'm going to do, I'll bring this t to the left hand side. So K1 into T equal to ln A naught by AT. A naught by AT is AT, I'm sorry. Now what I'm going to do, I'll take the reciprocal of this. If I take reciprocal, we should put negative sign in front. Or if you multiply by minus 1 both sides, minus will come to the left hand side. That's all. Minus K1 into T equal to ln, I'll write AT in the numerator and A naught in the denominator. We have taken reciprocal. Okay. Or see the left hand side, we have log A by, suppose you take this as A and this is B. We have log A by B. Log A by B can be written as log A minus log B, logarithmic rule. So we can write this as ln AT minus ln A naught equal to minus K1 into T. Okay, now I'll bring this ln A naught to the right hand side. So we'll get, let me write the next page. So we'll get ln AT equal to ln A naught minus K1 into T. Students, observe carefully. Now I am not having just A concentration. I am not having just AT. I am having logarithm of AT. Ln AT is there. If I plot, see this equation, this equation looks like a straight line equation. Y is equal to mx plus c. This equation is similar to the equation of the straight line. So if I plot logarithm of a, ln a, students observe carefully, I am not plotting a, I am not plotting at, I am plotting ln of at. If you plot ln of at in y-axis and time in x-axis, okay, in this case you will get a straight line with a negative slope. Okay, because m is minus k1 here, m equal to minus k1. You'll get straight line with a negative slope. So in first order, we'll get straight line with negative slope if we plot logarithm of a versus t. Logarithm of a versus t, if you plot, you'll get a straight line. Is this clear, student? Any doubt? If you plot a versus t, what type of graph we'll get for first order? See the difference, student. Note the difference carefully. If I plot a versus t, I'll get exponential decrease. If I plot ln a versus t, I'll get straight line with a negative slope. And what is the slope? Slope is equal to minus k1. So if you know the slope, you can calculate the k1. K1 equal to negative of slope of this straight line. Is this clear, student? Any doubt? Hello? Students, is this clear?
Yes, sir.
Yes, ma, take note. Then suppose if you plot the same quantity with this equation, say k1 equal to 2.303 by t log base 10 initial concentration of the reactant A by the concentration of the reactant at time t. Now I am taking logarithm of base 10, not simple ln. Logarithm of base 10 is there. So I'll bring this quantity to the left hand side. I'll get k1 into t by 2.303 equal to this. You can write it as, it is a by b, so I can write it as ln a naught minus log base 10 at, log a naught by log at. I'll bring this log at to the left hand side and this quantity to the right hand side. Okay, so what we'll get? Log base 10 at equal to log base 10 a naught. Students, if you find any difficulty, you please tell me. Minus k1 by 2.303 into t. Is this clear? Students, is this rearrangement clear? Any doubt in this? Instead of ln, we have log base 10 here, that's all. Now, if I plot, see, this is also similar to the equation of the straight line y is equal to mx plus c. Y is equal to mx plus c. So, if I plot log base 10 a in y-axis, log base 10 at in y-axis and time in x-axis, will get a straight line with the negative slope as before. But now slope, see, this is the slope. What is slope? Now the slope is equal to minus k1 by 2.303 or k1 equal to minus, okay, 2.303 times slope. Note down. K1 equal to minus 2.303 into slope. See the difference. See the difference. First we plotted a versus t, then we plotted ln a versus t, then finally we have plotted log a versus log base 10 a versus t. Okay, let me just show everything in one slide so that you'll get the clarity. Students, observe carefully. Now I am going to show you all the three graphs together. See, first let me show you the plot for AT versus T. For first order reaction, AT versus T will appear like this. It is an exponential decrease curve. Then if I plot ln AT versus T will get straight line with a negative slope. In this case, slope, from the slope you can calculate rate constant. Rate constant is nothing but negative of the slope of the straight line. You find the slope, change the sign, you will get K1. Now if I plot log base 10 AT, see the difference, log base 10 is AT versus T, you will get straight line with a negative slope. Here K1 can be calculated by multiplying minus 2.303 times slope. Okay, see the difference. So whenever a graph is given, you should see the graph carefully. See the y-axis, see the x-axis carefully, whether it is given A versus T or ln A versus T or log base 10 A versus T. Depending upon that, okay, you have to calculate the rate constant carefully. Is this clear, student? Any doubt? If you find any doubt, please tell me. Hello? Okay, then let me introduce one more term here, then I stop, student. Degree of dissociation. Degree of dissociation. What is meant by that? See, I have some reactant A which giving product B, okay, in a first order reaction. It's a first order reaction. In a first order reaction, how to calculate degree of dissociation? Right? Listen, student. At time t, see, the initial concentration of the reactant is A naught. After time t, the concentration become A. Right? This is concentration of A at time t. Now, from A naught to AT, some amount is reacted, okay, some amount at time t. Right? What is degree of dissociation? Degree of dissociation is nothing but, okay, listen. Suppose if I take 1 mole initially, from 1 mole of the reactant.
Ashika is asking something in the chat box.
Pardon, ma? Pardon? Hello?
Ashika is asking something in the chat box, sir.
No, a little louder. I couldn't hear your voice carefully, clearly.
Sir, Ashika is asking something in the chat box, sir.
What, ma? What, Ashika? I didn't notice that. 1 second. Can you send
Sir, am I audible?
In call message. 1 second, student. Sir, for the first graph, what is the rate constant formula? Okay. For this graph, okay, for this graph, right? Students, I have given this expression AT equal to, we derived it actually, AT equal to A naught into e power minus K1 into T, okay? See, at one step we derived this. Listen, from the same rate constant expression, I told you to remember 3 equations, correct? They are all, from one equation to another equation you can easily convert. Okay, they are all actually one and the same equation, right? We are making some conversion, that's all, right? See, for the first plot, from this equation we are plotting AT versus T. For the second case, A ln AT equal to ln A naught minus K1 into T. From this you are plotting the second one. Then third one I have given already. Instead of ln, you put logarithm of base 10 A, logarithm of base 10 A naught minus K1 by 2.303 into T will come. Is this clear, Ashika? Yeah, good. Actually rate constant expressions are one and the same, but for plotting different quantities, okay, we are making some change in the rate constant expression, that's all. Now, what is degree of dissociation? Students, observe carefully. Suppose if we start the reaction with 1 mole of A. Students, observe carefully. If you start a reaction with 1 mole of A, right, then at the time t, how many moles get reacted? That is nothing but degree of dissociation, right? Okay, so now, or I can say the other way, if the initial concentration is A0, at the time t, from the initial concentration, some concentration is reacted or some amount is reacted, therefore the final concentration become AT. Right? Now, what is degree of dissociation? Degree of dissociation, let me write this as alpha. Alpha is equal to what we had initially minus what we have at time t. Okay, so this is nothing but number of moles reacted divided by initial mole. Initial mole, let us assume this 1 mole. So alpha is equal to A0 minus AT, simple, right? Or we can also write this as, let me write the next page, or alpha is equal to, I'll keep this A0 as such, then in the place of AT, you know very well what is AT? AT is nothing but A0 into e power minus k1 into t. I have A0 here, A0 here, so I'll take A0 as common. So alpha is equal to A0, okay, into 1 minus e power minus k1 into t. Is this clear, student? Any doubt? How much mole is dissociated? Okay, take note. This is the expression for degree of dissociation. If you want, you can take. Okay, for NCERT examination is not required anyway. Yes, student. With this, we have completed first order reaction. In the next class, we will discuss some interesting cases of first order reaction. Okay, suppose if gaseous reactants are involved, what should we do? Liquid reactants involved, what should we do, right? So like that, we'll discuss different cases in first order. Once we finish that, we'll discuss second order reaction, right? Yeah, I stop here.